This lecture is going to be on kinetics. There should be several lectures on kinetics. This will be the first of maybe 3 of them. I'm going to try and keep them 30 to 40 minutes long, and it'll take a little while to get through all the material. But anyway, we'll just start out by talking about the rate of the reaction. And if you think about it, it's going to have to be something per unit time, right? Something per second, something per minute. In this case, we're going to be looking at the change in concentration versus time. So change in concentration versus time. And we'll be looking at different chemical reactions. Some of them will be very fast, some of them will be slow, and there's all kinds of reasons for that. And we'll look at all kinds of details about the order of the reaction and what you can predict from that and so on. All right, so then we'll say that the rate is going to be equal to the change in the concentration, delta is change, final minus initial, divided by the change in time. That looks bad there, hold on. Okay, and first question would be how to increase the rate of a reaction. So how to increase the rate of a reaction. And if I had you in class, you'd be giving me a few answers here. How about adding a catalyst? That can speed up the rate of the reaction significantly. Sometimes reactions don't even seem to go at all. You throw a catalyst in there and then you get a nice speedy result there. Also, you can increase the temperature. Of a reaction. That'll speed up the rate. Also, you can increase the concentration. Now, not everybody, would think about this intuitively, but maybe you've had some experience with it in the lab. If you throw some extra reactant in there, your reaction will actually speed up. All right. Now, if it's a gas phase system, you can increase the pressure of the reactants, and that means that they'll be closer together. The frequency with which they collide and react would increase, function of pressure. You could do that by decreasing the volume of your sample. And finally, you can change, if it happens to be a molecule that's a reaction that takes place on the surface, you can increase the surface area. To increase the rate. And you can maybe relate to that in the kitchen. If you cut up your potatoes and then cook them, they're going to cook a lot faster, so you've got the heat affecting all the surfaces of the smaller pieces, that kind of thing. So you can maybe increase the process by doing that. All right, well, we're going to look at most of these ways to increase the rate of the reaction. But we need to look at some details first about the rate, and that's really the first subject here for kinetics. We can pick a reaction, and this is a gas phase reaction, 2 N2O5s decomposing to form 4 NO2s plus O2. And we can talk about the rate of each one of the components in the reaction. So you can say the rate of decomposition of N2O5. That would be equal to, you put a negative sign in there. That's the convention if it's a reactant that's disappearing in time. And then you're going to say that delta for the change, so the change in concentration of N2O5 divided by the change in time. Then you can also talk about the rate of formation of O2. And O2 is a product, so we're going to have a plus sign to indicate that it's being formed. And we'll look at the change in oxygen in time. So it'll start out with 0, and then it'll go up to some value, some concentration value for oxygen. And then you can also talk about the rate of formation of the other product, which is NO2. And we'll say plus delta NO2 divided by delta T. All right, so then what is the relationship between them? The relationship has to do with the coefficients in the balanced chemical equation. So if you looked at a graph of concentration versus time, and let's make these numbers proportional to the coefficients here. So you get 1, 2, 3, 4, like that, and 0. And then this would just be some unit of time, seconds or minutes, whatever. All right, so the N, you have to go back and look at the balanced, hold on here. You have to look at the balanced equation. You see that it's a 2N2O5. So if you start at 2 for the N2O5, in time, the N2O5 concentration is going to decrease because it's a reactant and it's going away, right? It's disappearing, it's forming products. And then the O2 has a coefficient of 1 in front of it. So it's going to start out with 0 concentration because it's a product. There's no product present in the beginning. And then it'll come up to 1. This is all just relatively speaking. That should be 1 right there, just based on the ratios. And then for the NO2, the NO2 has a 4 in front of it, so you're going to get 4 times as much NO2 as O2 during the rise of the product formation. So the one in blue is the NO2, the one in red is the O2, and then the one in black is the N2O5. Like that, okay? So at any point in time, you can look at all of these ratios here. So this would be the decrease of the reactant. You got some of the oxygen already grown in and 4 times the amount of the NO2, like that. So you can always compare, you can always compare the rate of the reactions, or the different components in the reactions. And for this one, we might say that the change in the O2 concentration versus time is equal to, so if the O2 is growing in with a coefficient of 1 and the N2O5 is decreasing with a coefficient of 2, then the rate that the O2 grows in is going to be half the rate of the N2O5 decomposition. All right, then we look at the oxygen again, and now we see that the rate of the oxygen is going to be much slower than the rate of the NO2. So if it's a 4-to-1 ratio, we'll say that the oxygen is 1/4 the rate of the NO2 rate. So you have that relationship. Then you can put all this information together. And let me write the reaction again, which is 2N2O5 forming 4 NO2s plus O2. And take this rate information and say the rate of the O2 is -1/2 rate of the N2O5 decomposition, which is also equal to 1/4 the rate of NO2 versus time, or concentration versus time. Now I can rewrite this again, and this time put them in the order of the components in the reaction. So I can say -1/2 rate of N2O5 is equal to 1/4 the rate of NO2, which is equal to 1/1 times the rate of O2. And if I do it this way, then there's a relationship between the coefficient 2 and the 1/2 here, the coefficient 4 and the 4, and the coefficient 1 and 1. So if you want to look at the relative rates, which is what these are called, relative rates, so one with respect to the other, look at the coefficients, and if it's disappearing, you're going to put a negative sign there. If it's growing in, it'll be a positive sign. It's just 1 over the coefficient times the rate of the substance. All right, now we're not going to spend too much time on that, but there's always examples in the book on this where you want to know what the relative rates are. Okay, so then the next slide here, the next whiteboard, we want to look at some data, and this is going to be for the oxygen that's growing in for this reaction. And we can look at a table here, T, time in seconds, and then what's the O2 concentration, and then finally we want to calculate the rate, and the rate is going to be in units of molar per second. So we can look at 0.0 seconds. The amount of oxygen is going to be 0 because it's a product and it hasn't grown in yet. We can look 1200 seconds later, and the concentration of oxygen has grown to 0.0025 molar. And if you want to calculate the rate associated with that 1200 second time interval, you're going to look at the change in concentration, which is 0.0025 minus 0, divided by the change in time, which is 1200 minus 0. And the rate here is 2.5 times 10 to the minus 6, and the units are molar per second. Molar is for the numerator for the concentrations, and seconds is for the denominator there for time. Then let it go another 1200 seconds to a total of 2400. You get 0.0050. The rate here will be 0.0050 minus 0.0025 divided by 2400 minus 1200 seconds, and you get the same number, 2.5 10 to the minus 6 molar per second. Keep going. Now you have a total of 3600 seconds after the next 1200 second interval. You have 0.0070. So to calculate the rate here, it's going to be 0.0070 minus 0.0050 divided by 3600 minus 2400, and that is equal to 1.7 times 10 to the minus 6. That's a 1 right there. And then you can look at the next one, 4800, and that's going to be 0.0080. So what do you see here? The concentration of O2 is starting to slow down. That's because the system's running out of reactant. So you have 0.0080 minus 0.007, and then divided by 4800 minus 3600. So this is 8.3 times 10 to the minus 7. Now you could do one more. You could say 6,000. I don't have the numbers for it, but I think I have the rate, which I can add to this table, that value a little bit later. Okay. All right, so then we can take this information, and first we'll just look at the numbers. You see that the rate of the reaction is slowing down, right? So you start out with 10 to the minus 6, you end up with 10 to the minus 7. the numbers are decreasing monotonically up down to 8.3 10 to the minus 7 in time. So if you're going to graph this data, it would look like this. Here we're plotting the O2 concentration versus time. And you got seconds here, so put that in. Then you have 0, 1200, 2400, 3600, 4800, and then 6000. 6,000. And if you look at that data, which I just scrolled off, in fact, I better come back to it there so I can see it. And we have concentrations going up to 0.008. So 0.001, 2, 3, 4, 5, 6, 7, 8, something like that. So 001, 002. To 008. All right, so the first data set is 0 and 0. Then we have 1200 seconds, and it goes up to about 0025. 2400 seconds, it's 005. 3600 seconds, and it's 3600 seconds, and it's 007. 4800, it's just going up to 0.008, and if we kept going to 6000, it would end up something like that. So we've got a curve here. Excuse me, and clearly you can see how it kind of levels off to zero slope, and that would correlate with the reactant concentration going to 0. So there's no more oxygen to make because there's no more reactant. All right, now we can pick some points on here. And how about if we did 007 and 005 like that? And we can calculate the rate graphically. So we can make our little triangle here. And we want to calculate the slope associated with the line that connects those 2 points. So you got 0.0070 minus 0.0050 on the y, and then divide that by 3600 minus 2400 on the x, and that's 1.7 times 10 to the minus 6. And this that's rate, so it'd be molar per second. And that corresponds to the rate of O2 over that time interval. All right, now that's an average rate because you've certainly got points in between those two that we're looking at. And so the average rate would just be associated with the line that connects the points. And it's referred to as the average rate. But those of you who had calculus, I'm not assuming that everybody's had calculus, but if you have had calculus, you know that the instantaneous rate is much better at being more precise with the changes. And so the instantaneous rate, if you've had calculus, you know what I mean. You'd pick a point on the curve, and then you would draw a line that's tangent to that point, and then you'd have a slope associated with just 1 point, and then that slope would be changing in time, and that's referred to as the instantaneous rate. And instead of calling it delta, we use a symbol D. That's a symbol that's used in calculus. So it's dO2 instead of delta O2 divided by dt. So D means an infinitesimally small change. I don't think I can spell that. I'm just going to say very small infinitely small change. Much smaller than the 1200 seconds we're referring to. So I'm just pointing that out because when we say the rate of the reaction is proportional to concentration, it is the instantaneous rate that you would use to move forward with your mathematics to calculate what's called the integrated rate law. So there's a difference between the average rate and the instantaneous rate, and it's just your evaluation of the change in concentration over much smaller intervals of time. All right, don't worry about that. I'm not going to test you on calculus. I am going to do some calculus, but I'm not going to test you on it. Just those of you who've had it, I think you would probably be interested in it. You know, why are you spending all these semesters learning calculus? Well, you might as well see some chemistry applications for calculus. So that's my strategy there. All right, now we're not there yet. We want to talk about two different ways to express the rate of the reaction. And the first one we've discussed, we can say change in the concentration of A, whatever the substance is, divided by change in time, or we can use the symbol D instead, dA dt. There's another way to talk about rate of the reaction, and this is the rate law. We're going to spend some time on the rate law. And in general, I'll just give it to you and kind of show you how it works. So we say the rate will be equal to K. K is the rate constant. Hold on, let me back up here a little bit. Give you an equation first. Excuse me. So if we had the reaction A moles of A plus B moles of B forms C moles of C and D moles of D, for example. We can say that the rate of the reaction will be equal to K, which is called the rate constant, times the concentration of A raised to the power M. And then that's multiplied times the concentration of B raised to the power N. And if we had another component, it would be not raised to the power O, but it might be raised to the power P. So if we had three components, it would be M, N, and P would be the superscripts in that, or the powers in that expression. All right, so let me make some notes here. K is called the rate constant. That's a number that is particular for that reaction. M, N, and P are referred to as the individual orders of the reaction. And then we have the relationship that M plus N plus P is equal to the overall order for the reaction. And a very important note here is that there's no relationship between the order, those powers, and the coefficients in the balanced equation. So that's a very important statement that we make now. There is no relationship between the individual orders and the coefficients in the reaction. Okay, and that's almost true. It's a little bit of a lie. Later on, I'm going to show you that there is, in fact, some connection, but only under certain circumstances. We certainly don't want to start out with that discussion, so we'll come back to that. All right, now, I just want to give you some examples here. so you get a feeling for it before we go into details. So here is an example for a first order reaction. You have the molecule cyclopropane, C3H6. This is in the gas phase, and it all by itself will decompose to form CH2, CH, and CH3, and that's in the gas phase as well. So on the left-hand side, the name of the molecule is cyclopropane, and then we have propene on the right. So cyclopropane is actually a molecule that's got a triangular shape. The corners of that triangle are carbon and hydrogens, 3 times in a triangle. And then it opens up into this linear molecule. Which is more stable. So you might heat it up and it'll kind of just fall apart. That ring will open up and it'll go to the linear molecule that's got the single bond. So the rate of this reaction is going to be K times the concentration of what's on the left, which is in this case a cyclopropane, and that's raised to the first power. So that means if it's got a 1 up there, then that's going to be first order. Okay, and how do you know that the rate is proportional to the concentration, to the first power? You do an experiment to figure that out. You can't look at the coefficients, even though the coefficient's 1 in this example. That's not it. You actually have to do an experiment to show that that's true. All right, then an example. There's 2 examples for second order reactions. The first one is acetone, CH3CO, that's a carbonyl group there, CH3, aqueous, plus I2, aqueous, plus H plus aqueous, and that forms iodoacetone, so CH3CO, CH2I, and then you have HI, whoops, that's not an H, HI, and both of these are aqueous, AQ and AQ. We're not space there. All right, so then the rate law for this reaction turns out to be K times CH3CHO. Oh, wait, I got the wrong one. Sorry about that. Acetone. So K times CH3COCH3, the acetone, raised to the first power, and the H plus raised to the first power. Now, they do match the coefficients, but that's not what we're doing. We have this information from experiment that, the acetone, the rate is directly proportional to the acetone concentration and directly proportional to the H+. Notice the I2 is not even in the expression, so that would be I2 to the power 0. You could write that, but nobody ever does. Oops, a mistake there. I2 to the power 0, but of course that's equal to 1, right? So, if you just looked at the reaction, you might say that all 3 components should be first order, but that's not the way it works out at all from experiment. The other example, so that's A, and this example is B for second order. This one is CH3CHO, that's in the gas phase, forming CH4 methane, gas phase, plus CO, gas phase. And for this one, the rate of the reaction is K, the rate constant, times CH3CHO squared. So how did we get that? There's no 2 coefficient there. So again, the order, the individual order is not related to the coefficients, and you have to figure out that there's that square dependence on the concentration of the formic. What is that thing? That would be methylformate, I guess. Right, so you'd have to figure it out from experiment. Formaldehyde. I got to work on, I've forgotten what the name of that compound is. All right, here's an example for a third order reaction, just for comparison. This is 2NO in the gas phase plus 2H2 in the gas phase, forming N2 and 2H2O. The rate law for this reaction is K. Rate equals K times NO squared times H2. So you get 2 plus 1 here is equal to 3, and that's the reason why it's a third order reaction. And again, that information is determined experimentally. Okay, so let us start with a new page, and on this page we will look at a simple example for determination of the rate law. From experiment. Okay. So we oftentimes take our data, our experimental data, at very early times, referred to as the initial concentrations, to get an initial rate law. And that's because if we don't do that, the reaction may go off and form some side products or something, and the kinetics might change. So it's just a term. We want to look at the change in the initial concentration. Versus time. So here's our example again. And it's 2N2O5. I think I'll leave off the G for gas. It's all gas phase. And it forms 4NO2 plus O2. And the rule here is that the number of experiments that you have to do to get the order is going to be equal to the number of reactant species plus 1. So if we have one molecule on the left, N2O5, we're going to have to do 2 experiments in order to figure out the rate law. So you have 2 experiments, experiment 1 and experiment 2, and we want to make our measurements of the initial concentration, and that's of the N2O5, and then the initial, that's messy, sorry. The initial rate. Now we know how to calculate the rate. So it's the change in concentration divided by the change in time. So we've already done that, and we've calculated the initial rate associated with the particular initial concentration. So if we start with 1.0 times 10 to the minus 2 molar, we're going to find, you know, we have to do the graph, and we got to take the slope associated with, you know, 2 points. on that curve, and we have to figure out what the rate is. So it turns out to be 4 at early time. So 4.8 times 10 to the minus 6. And the units here are molar per second. Okay. And then we go back and we do a second experiment, and we start with twice the amount of N2O5. And it turns out that the rate here is 9.6 times 10 to the minus 6. All right, so what do we see here? If you double the concentration, the rate of the reaction doubles, right? You go from 4.8 to 9.6. That's not always the case, but that's the case for this reaction. So if I double the concentration and the rate doubles, which is what we see here, then M is equal to 1. And that is first order. Okay, so I said we have to figure out the order from the experiment, and that's what this is. So we would say then that rate is equal to K times N2O5. Oops. 5 raised to the first power. And oftentimes we do not write the 1, so we would probably end up saying K times N2O5 for the first order reaction. We're not really finished yet. We have to know the value of K because the rate constant says something about how fast that reaction is moving. So we want to solve for K here next. Let me do that in a different color. Solve for K. And K in this particular case will be equal to the rate, I'm just solving for it, divided by the concentration of N2O5. And we can take our information. Now, let me back up to the table here. We can pick any experiment and use the data in the experiment to calculate the value of K. So I'm picking experiment 1, but if I had picked experiment 2, I would have gotten the same value of K as long as I am correct in my rate law. So I can say that K equals, from experiment 1, 4.8 times 10 to the minus 6 molar per second, and then I'm dividing that by 1.0 times 10 to the minus 2 molar, and then I'm going to get the rate constant K is 4.8 times 10 to the minus 4 seconds to the minus 1. All right. Then you take that information and you put it all together. This is the final answer. I ask you for the rate law. I want this. Rate is equal to the rate constant, 4.8 10 to the minus 4 seconds to the minus 1 times the concentration of N2O5 raised to the first power, but you don't have to write the 1. So that's your answer. That's the answer. That's going to be the rate law. All the parts to it. That's not so bad. You can pretty much look at that and say, if the concentration doubles and the rate doubles, then it's going to be first order. Okay, that is the sense of it. It can get more complicated when you have more than one reactant, and when it's not first order, it's not always obvious there. So, but for this very first example, we just have one reactant. It's pretty straightforward. Okay, I want to do another example, but I don't want my video to be too long. I think it's been going for a while, so I'm going to stop it. And this will be called Kinetics I, and we'll start up with Kinetics II for the next one. Oops.